Hey everyone, I'm Venkatesh, a postdoctoral researcher at TU Delft, and today I'm going to present our work on efficient exemplar selection for complex reasoning. This work was carried out in collaboration with Kiran, Raghuram, Saurangshu, and Krishna from IIT Kharagpur and Abhishek Anand from TU Delft. So, large language models have made tremendous strides in natural language processing tasks in recent years, including complex reasoning tasks. And here, complex reasoning refers to tasks that require compositional reasoning or numerical reasoning or text and tabular reasoning. And LLMs have emerged as general purpose engines which can do this wide range of tasks without fine tuning or multiple fine tuned components. And this has been made possible through emergent capabilities such as in context learning, where in context learning you just provide few short examples and demonstrate the task to the model, and the model automatically adapts and learns to do this new task. And in this paper, we sort of call this few short examples as exemplars, where each exemplar is a triplet consisting of a question, an answer, and the explanation or reasoning required to arrive at that answer. So careful selection of exemplars is really important as it affects the final task performance. It is important to ensure that the exemplars are diverse, sort of like elucidating the nature of the task, and also they have like positive correlation with other exemplars in the set. So the literature has a lot of papers trying to carefully select this exemplars. A very simple way is to like sort of manually select these exemplars, but this is very cumbersome and time consuming, and there is no way to know that these exemplars are really good as it's subjective. So several papers have sort of proposed valuing each exemplar with respect to the test example, and this falls into the category of dynamic exemplar selection. But a drawback of dynamic exemplar selection is that it adds to the computational cost during inference, where you have to sort of score through thousands or hundreds of thousands of pools of training examples with respect to each test example. And also, dynamic exemplar selection has a drawback that it does not model the interaction between the exemplars. Because exemplars may have positive or negative correlation with respect to other exemplar in the set. So a very good exemplar paired with a bad exemplar or another good exemplar which sort of like has a negative correlation to the current exemplar could bring down the overall task performance. An alternative is sort of static exemplar selection, which is very computationally efficient because you sort of select a set of support examples for a task which you believe are representative of the task and use it throughout. So this does not add to any additional computational cost during inference. And if you want to be more efficient, you can also sort of cache the attention values for this exemplars so that the LLM need not compute them for each test example. Um, and they also offer attribution because you can sort of attribute the performance on a certain test example to a handful of training examples. But static exemplar selection has been mostly manual, and the only principled approach was proposed in Lens. But Lens sort of proposes a value function that evaluates each exemplar training example exhaustively. This is very time consuming, though this is one time. And also, they also do not model the interaction between exemplars, which brings us to the same drawback stated earlier. So in this work, Explora, we propose an algorithm, Explora, where we focus on static exemplar selection. We come up with a principled exemplar selection mechanism inspired by explore exploit paradigm and multi-arm bandits. And this figure sort of provides an overview of this approach. So first, what we do is like we take this large pool of training examples, hundreds of thousands or thousands, and we sort of first cluster them, and we sort of like form 5 clusters because we want 5 short examples. And now from each of this cluster, we sort of sample with replacement. We sort of sample a few short example, basically the triplet with replacement, because we want to model the interaction of an exemplar with other exemplars. And so sampling with replacement will make sure we capture multiple interactions for the same exemplar. And next, what we do is like now we want to value this exemplar subsets. So we call them exemplar subsets because each subset has a set of exemplars. And we don't want to do this exhaustively like prior approaches. So we sort of come up with the explore exploit paradigm, again inspired by multi-arm bandits. And we frame this problem as a top-M arm selection problem, similar to top-M linear stochastic bandits. And we want to select sort of like top-M or top-K exemplar subsets from this. and we'll elaborate more on that later, why we do that. So to sort of like come up with this explore exploit paradigm, we sort of need an objective function. And here our objective function is LLM loss, where the loss is calculated with respect to the end task performance using a metric such as accuracy or exact match. And we sort of like cannot evaluate the LLM loss for each exemplar subset as it is again exhaustive. So we come up with a surrogate model which sort of estimates this LLM loss, and that is denoted by sigma here. And it's basically a weighted linear estimator. And we sort of want to learn this weights to our explore exploit mechanism. So we estimate the loss and then we carefully sort of like sample the LLM loss only for few exemplar subsets by carefully selecting them. And we sort of like readjust the weights by calculating the approximation error. That is the difference between the actual LLM loss for the subsets and the estimated LLM loss. And this goes on through several iterations till finally we sort of get the set of top M exemplar subsets, set of top M exemplar subsets. And to further dive deep into Explorer, the loss modeling function or the surrogate is sort of like now shown on the screen. So this is denoted by sigma. It can be sort of seen as a loss estimator or a loss approximator. It is sort of like a linear model, like linear stochastic bandits, where alpha here refers to the weights and EIJ refers to the feature matrix. So the feature matrix is computed by sort of modeling the interaction between the exemplar in the exemplar subsets, each exemplar in the exemplar subsets, and the validation examples. So which is sort of shown on the bottom of this slide, where basically we compute the cosine similarity between ith exemplar and the ith validation samples, and we sort of aggregate it across the validation samples. And basically, so now the weight sort of denotes the importance of a certain exemplar, its contribution to the LLM loss. So alpha I denotes the ith exemplar's contribution, and this is low if this particular exemplar is important and leads to overall improved loss estimate. Because we are modeling the LLM loss, so we sort of want the overall estimated loss to be low. So lower alpha I indicates it's an important exemplar, and higher alpha I indicates that it's not. It's sort of like a negative exemplar. Now to sort of like put this all together, we sort of have this sort of like loss modeling function, sort of this approximation error. This equation denotes the approximation error. And this is the step where the alpha i's are updated. And we sort of use linear least regression to update alpha I, just like in linear stochastic bandits. And to sort of break down this equation, we sort of have UT, which is our current estimate of top M exemplar subsets. So UT is a set of exemplar subsets, and VT is basically the rest of exemplar subsets. So we had this global set of exemplar subsets, which we formed after sampling with replacement. And UT and VT are initially sort of initialized from this at random. And as the algorithm runs, the estimate becomes better. So VT is really large and UT is a small set. It could, for example, like M could be 10, it could be top 10 exemplar subsets. And the first part of the equation denotes basically the approximation error we discussed previously, where we sort of like estimate the loss using sigma for a certain subset from, let's say, the global set where we sample with replacement. And we do this, and then we also estimate the true LLM loss for this subset by sort of like evaluating on validation samples. And this LLM calls is sort of like performed only for the exemplar subsets in UT, which is our current estimate of top M exemplar subsets. So as we can see, this is equivalent to arm pulling in multi-arm bandits, and we do not exhaustively evaluate, but it's a sort of rather limited to the small set of UT. But this sort of like is more of the exploit part of the algorithm. We also want to make sure we provide a fair evaluation to other subsets in VT, which is all the subsets not in UT. We want to make sure that there may be few subsets that were misassessed in the beginning, but we sort of give them a fair chance. So we sort of also do negative exemplar sampling, which is sort of one of the novel parts of Explorer. So we sample few exemplar subsets from VT in a principal manner, which have and we sort of like also reduce their approximation error. So these subsets later have a chance to make it to UT. So basically based on the approximation error at each iteration, we sort of check the estimated loss. And if an estimated loss in VT is sort of lower than an estimated loss of an exemplar already in UT, we sort of swap them. So this way the UT estimate becomes better. And then at the end of the iteration, we sort of compute these approximation errors and adjust the alphas. So then the next iteration, we sort of get better estimates for UT and VT. And this keeps going on till we converge to top-M exemplar subsets. So the negative sampling is one of the novel parts of Explorer. And we sort of evaluate, we sort of in the end get top-M exemplar subsets, and we use this to evaluate on downstream complex reasoning tasks. And we do our experiments in a transfer setting inspired by mu transfer, where we sort of run Explorer on smaller LLMs, quantized LLMs like Llama and Mistral of really small number of parameters like 3 billion or 7 billion, and transfer them to larger models like GPT 3.5 Turbo. This is to sort of like reduce the costs associated with evaluating larger models. And we sort of show this paradigm that Explorer is model agnostic. And here we observe that, for exemplars transferred from Mistral, we sort of outperform all the existing baselines, static exemplar selection approaches like Lens and other approaches. And we also observed that we outperform dynamic exemplar selections approaches, which was a surprising result. And we observed that Explorer transfers really well. For example, when transferred from Llama or when transferred from Mistral, overall they lead to improved performance compared to other baselines. And we also observe that Explorer is more robust, as in the variance across test examples is like really low. This sort of shows that selecting support examples which are representative of the task leads to more stable task performance. And we also sort of compare the resource efficiency of Explorer, which is one of the cornerstone of this work. We observe that, as seen in the first plot, that Explorer reduces the number of LLM calls to about 11% of the number of calls made in Lens, which is like a huge improvement. This is done, though this exemplar selection is done only once, we also want to make sure that it's resource efficient, and as it can be seen, the number of LLM evaluations are really low. And also, of course, the time taken to sort of select this exemplars is also low because number of LLM calls are low. And this is only possible because of our linear loss approximation modeling. Basically, this linear modeling, and also in addition, the negative sampling. Thanks a lot for your attention, and the code for exemplar selection and all complex reasoning evaluation can be found in the GitHub repo. And for more details, you can sort of contact the corresponding author or me. Thanks a lot.